So you guys can go ahead and join the Kahoot for today. And while we're at it, if you happen to be towards the sides of the room, maybe you want to come closer to the microphone, so it's easier to pick up your voices. I know our support team has have a lot of difficulty trying to transcribe what's happened. Okay, let me share the screen. You guys see it now? Yes. We had to turn off the blur in the background. Okay. Hopefully you can see the board too. It looks like it. So there's also a wireless mic here. So if you want to present using a wireless mic, just put the thing in your pocket and you can either clip it or whatever. Okay. I'm going to switch it off for now, but yeah, when you come up, you can do that. Okay, everyone in? Anyone not in who wants to join? Hey, who is our narrator for Kahoot this time? Who created the W5 deck? Winston? Is it Winston? Somebody say that in chat. Okay, no, that's autopilot. Okay, it's Winston. Winston, are you online or here in the room? Nope. Okay, Kahoot has said it's time to start, so we'll try to narrate it on our own, okay? Multi-select. Double points, oh boy. Which model is considered decoder only? Hopefully you get this pretty easily. Okay, so we have BARD as well as autoregressive language models as the answers for this. The other two are not. I mean, mass language models, just everything under the sun discussed in this class, so that's wrong. And BERT is the encoder model that we've talked about, so we'll go on from there. P/AC in front. Clyde and Liang in second and third. Another multi-select, another double points. Why are there more developments on decoder-only models? Fast fingers, guys. Let's go. Okay, so we have two answers here, and it looks like most of you also voted that way. Generally, less compute required. Certainly, that's the case. You don't have to do the encoding, and then better generalizability across domains. Okay. And E/ACC is still in front. Our graphics card has come to the front, and Nick is in third place. Another multi-select, another double points. If this is for the whole thing, that'll be very funny. What is a morpheme? I'm not sure why that's here, but it's. At least two more people, come on. Somebody marked it as a strong opioid, even though sometimes I feel like that, on a Friday afternoon. Yeah, so it's a meaningful unit of language that cannot be further subdivided. We can certainly multiply them together. In certain languages, we have a lot of morphemic complexity. So I guess this is in relationship to what we talked about with subword embeddings last week. All right, so let's keep on going. We've done their natural language processing. So we're still in the front here, Nick and Young, going up again. Our graphics card is getting replaced by its next generation. You know the drill, right? Yeah, okay. What are the reasons for using an integer versus float for quantization? These are long things to read. If you're behind, just mash the buttons. Maybe you'll get it right. Given the memory constraints of the type of float has less representation. Okay, I would have thought some of the other answers, but we want to talk about this. Please discuss on the general channel. You're willing to take a screenshot and then share, and then we can debate that. But the quiz says that it's the third one. Okay. All right, so let's see whether we get a change in their rankings. Okay. Nope, still the same. Tough round, 3 players lost their answer streak. Okay, true or false, okay? Also double points. Is it possible for distilled models to be quantized? You guys gotta be fast, there's only 2 options. Absolutely, okay. So it might have been a trick question, but it wasn't for our leaders. So we're going to go on. Quiz, multi-select, double points. Somebody had fun putting double points on all the questions. Quantization provides the following advantages. Hurry up. 9 seconds. 1 or 2 people haven't cheated. All right. Yeah, that's the same checkboxes I got. Okay, very good. Ooh, okay, our graphics card is back again, and Hannah and KL are catching up. Let's see, we got 2 more questions. Are they going to be double points? That's the question. And yes, in 8 and in 4. I'm grasping for straws. I have no idea. Oh, I guessed right. I'm shocked. Okay. So 5 of us got this answer. Ooh. NVIDIA. Okay, last one. Is it? Yeah. All right. What is true about distance supervision? I know someone in this room who should get this right. All right, so that is the key feature of distance supervision. And our winners for today are third place, AL, Y of Y making a surprise appearance, and A100. Congratulate all of our winners today. All right. Yes. Okay. So we have a team of folks, Arnav, Conrad, Disha, William, and Filbert. How many of you are here? 1, 2, 3, all of you are here. Oh, excellent, excellent. Okay, we actually gave you pretty good timing. Okay, only 15 minutes eaten up. Over to you. Can we get this out of the way? Can we actually make it go away? No, we have to put it somewhere. Okay.
All right. Okay, so welcome to this pretty loaded topic. So there's a bunch of things happening here. So we have scaling up, which I'll be covering. So I'll be covering on scaling laws, and training and parallelism will be covered by a few of the other speakers, and you'll see why it's such a big topic to cover. But yeah, let me start with scaling laws. And so today I'll be covering 2 papers. So the first paper is this paper called Scaling Laws for Neural Language Models, which was the one that initially did all empirical tests based on like all the different parameters that you can change and seeing how it affects your loss, essentially. And the second paper is one that's more recent, so it came out last year. And it talks about how we can, in fact, do better than the laws that were determined in the first paper. Okay, so before we start, maybe I want to show you this page, and hopefully by the end of my talk, you'll be able to understand the contents of this page better. So this page is sort of like an excerpt from a paper that some researchers did. And basically their main question was, given a certain amount of compute, let's say you have like, so over here they had 18 weeks on 384 A100 GPUs. So given this amount of limited compute, what's the best model you can train? So the best model has like a bunch of different stuff, right? So you can change your data set size, you can change the number of layers that you have, you can change the number of some other dimensions in your model, you can change your architecture. So basically, the main question is, what do we choose for all of these parameters, right? So yeah, hopefully by the end of my talk, you'll be able to better understand this paper and apply these in your own models in the future. So first, let me begin with what scaling laws are. So scaling laws basically are empirically determined, but they're very precise laws that govern how these different variables essentially affect our final test loss on our model. So we can change our model size, we can change our data size, we can change our compute, so how much time we spend on the GPU training our model. We can even change our model shape, so change the amount of layers while keeping like some other parameters constant. And yeah, so this is what this first paper talks about, which is all of these laws. So there's a whole bunch of laws I'll be talking about, and my slides are basically all graphs showing you what all of these laws mean. Some motivating questions that were behind this paper was one that I shared just now, the one by on the Hugging Face website, which is given a limited amount of compute, what is the best model we can train? So that's the first one. After that, it is given some data of like some early data of a machine learning model's like loss. Can we predict how it would do given you train it even more? So let's say you train it for like a few epochs and you look at the test loss after those few epochs. Can you what it would do if you train it for even longer? Another one is how can we avoid overfitting? So if we have a data set that's too small and we train a huge model on it, obviously there's going to be overfitting. So how do we prevent this? And lastly, how do we transfer this knowledge of language models to different data distributions and tasks? Yeah, so this is the crux of this paper. And maybe I'll start by explaining these graphs from right to left. So on the y-axis for all of these is our test loss. And what they did was vary one of the parameters, or what I should say one of the variables. So in the rightmost case, they varied the number of parameters in the model while keeping the data essentially such that the loss caused by the data is zero. And also they sort of assume infinite compute time. So once we do this, we can see that with increasing parameters, and by the way, the test loss is on a log scale. So since it's a linear straight line down, it's basically a very nice power law that governs that, okay, if we keep our data and if we keep our data set size constant and our compute essentially infinite, if we increase our parameters, it's gonna do better in this very precise power law way. And they did the same for data set size. So here they kept the parameters really big, so they trained it on the biggest model that they had, and they essentially gave it infinite computing again. And here they applied early stoppage. So this is where they basically stop the model when it reaches its minimum test loss. And lastly, we have the graph on the left, which is a bit more complicated. So here they basically plot all of the blue lines that come from above are all of the models that they train. And if you think about it, our compute is proportional to the number of parameters we have times our data set size. And so when we take the log of this, it basically becomes log params plus log tokens. And so it's basically sort of shifting our graph on the scale. So that's why you can see all of the graphs, all of these plots look similar, but they're just shifted. And what they found was when you take the minimum of this, the same laws also apply for compute. Yeah, that's the crux of this paper's results. And yeah, like I said, basically each of these graphs is assuming that that is the only bottlenecking point of the model. Oh,
quick question.
Yeah.
I mean, the graph tend to be linear.
Yeah. So this is on a log scale. Yeah. So the test loss, as you can see, is 2 to 3 and 4 to 5. It's decreasing. Yeah. And the actual empirically determined thing is also here. Yeah. Let me fix this slide. But basically, this is where is the okay. Basically, this says that architecture is essentially less important. So if we look at the bottom few graphs, what these graphs essentially say is that they're changing the shape of the model. So here they change like some ratios of the feed-forward dimensions to the model dimensions, and then they change like the layers in the model. But in each case, they kind of keep the parameters constant. So in this case, they tested like 3 different parameters, keeping it constant. And what they found is there's sort of this basin where if you keep your shape within that basin, it performs relatively around the same. So your loss percentage is only like a few percent. So what this says is that your architecture is actually less important when it comes to your loss as compared to your model size, your model, your data set size, and your compute, which are all power laws. And basically, they also found out that the conclusion of this is that architecture is less important until the architecture itself is the bottleneck. So this is where they compare LSTMs to transformers. And you can see that LSTMs, no matter how much you change the parameter size, whatever you change, it will never do better than transformers because LSTMs themselves are the bottleneck. And on the right graph, how this is shown is, so the blue graph, the blue lines are all transformers and the left lines are all LSTMs. So you can see LSTMs tend to plateau after like 100 tokens or something, but transformers continue to do better. So because LSTMs can't capture long-term context. Yeah, so transformers tend to do better throughout every single thing that you can change as compared to LSTMs.
You think the architecture is a bottleneck?
Yeah.
You mean the capabilities?
When you say the architecture is the bottleneck,
Yeah.
you mean the capabilities of the architecture rather than the micro, like the fine detail, right?
Yeah, pretty much, yes. So it's basically changing the whole system itself from a LSTM to a transformer.
Arnav, can you press L on the keyboard and then use the laser cursor?
Okay.
Yeah.
Okay, so now moving on to the third point, which is how do we prevent overfitting? So here we have 2 graphs. On the left is where we vary the data size and the parameters. And what we see is that, so you can see for smaller data sets, even as you increase the parameters, it sort of stays constant, the test loss. Again, this is using early stoppage. So this is where your test loss is at its minimum. So it's sort of not letting it go back up as you would expect when it overfits. So it sort of remains constant for smaller data sets, and we can see that for larger data sets, it doesn't overfit. And they plotted this on a curve that looks similar to this. But I'll give the conclusion in the next slide, which is basically that to prevent overfitting, you want your data set size to be larger than whatever that is. But the conclusion of this is it is a sublinear growth. So if you increase your model size by, let's say, 8 times, you only need to increase your data set size by 5 times. And that comes in very handy when you want to determine how you want to allocate your compute resources, which I'll cover in a bit. And lastly, they also looked at training steps and model size. So the conclusion of these 2 graphs is looking at the right graph, it basically says that even as you increase the number of steps that you train your model for, it only decreases your test loss by so much. It's quite little as compared to changing your parameters and changing your compute. So as you can see on the left graph, you're changing your compute, and the increase in optimal parameters is very drastic versus the steps. Yeah. And then the next one I want to cover is, so this is the question that we started with, is how do we allocate our compute budget? And let me go to the next slide first. So this is how they say you should do it. Their conclusion is basically train a really large model on a smaller data set size, while keeping this data set size to the constraints that we talked about earlier. But basically most of your allocation should go towards your model size. And yeah, so even as you increase your data size, you can increase your batch size that you process it in as well. And they found that this doesn't affect it as much. Yeah, so this is the answer to the question. Basically train a really large model. Even if you have lesser data, it's fine, as long as it doesn't overfit. Yeah, and then I'll be talking about the second paper and giving a very quick overview, because It's a long paper and I didn't get time myself to fully read it and understand it, but I got the gist of it and I'll be explaining that. And basically what this is talking about is we determined a few power laws earlier, but is it possible to beat this? And the way they beat it is by intelligently choosing your data. How do you intelligently choose this data? How they did it is they first classified it into easy and hard examples, and then they prune off a certain subset of your hard examples. But okay, first of all, how do we even determine what these hard and easy examples are? So maybe I'll draw it on the board. So let's say we have like a data set here that's like this one class, and we have another class over here. So we'll train a so-called teacher perceptron model that learns to classify these tasks. And let's say the boundary of this training comes out to be something like this. After that, we also train another model that is suboptimally trained. So we call this the student model. And we'll ask it to do the same classification, but obviously it won't be as good. So maybe it'll look something like this, for example. So let's say this is the student and this is the teacher. So the way we classify hard examples is basically by looking at the perpendicular distance that we have here, or the orthogonal distance. So we look at these two distances for a given data point. So let's say we're considering a data point that's here. We look at its distance to the student model, and then we look at its distance to the teacher model, and we compare this difference. Now, the reason we compare this difference is basically when it's very large, your student model has a lot more room for error. So it can move around a lot and still classify the point correctly. But let's say you consider something over here. So this distance is much smaller. And if it moves around more, if it moves around at the same level as the first one, it will start to misclassify your data point. So this is considered a harder example than this, because an easy example, you can have a larger margin of error. But for a harder example, you would need, you can only have so much error. Yeah. So what they did was essentially say, okay, we're going to prune off a certain amount of hard examples. And yeah, so that's what they did here. So one of their main findings was basically, it should say hard examples. It's always best to discard hard examples, but the best pruning strategy depends on the amount of data you have. So as you can see here on the x-axis, let me use the laser. On the x-axis here, we have the total examples per parameter. And this is again because of we want to prevent overfitting. So we have data like mapped to the parameters. And what they found was when you have lesser data, you want to keep more easy examples. Because if you want the model to be able to generalize when it's smaller on the easier examples, otherwise it'll basically get confused. Right. So as you increase your example count, you can start to include harder and harder examples in your data set. Yeah. And so the left-hand graph here is what they theorized. And the right-hand graph is they trained a ResNet 18 on the CIFAR 10 data set in this way. So they did all the pruning according to the theory that I explained earlier. And yeah, they found out that it sort of fits. There's a few, it's sort of in the general realm of what the theory describes. And yeah, so using this, they basically show that when just now we had a power law, which is this black straight line here, if we start to prune, we get better and better results, and it eventually tends towards an exponential law instead of a power law. So this is much more powerful than what we previously described. Yeah. And that is basically the end of my part. So any questions?
Questions?
Yeah.
Yeah, please go ahead.
Thank you for the presentation. My question is, how is the second paper? The main idea sounds like boosting. So maybe we can sample in the next iteration we samples with higher chance of getting error, right? So
Yeah.
instead of pruning the data, can we like adjust the sampling strategy for the sample data?
So you're saying essentially changing the way you prune the data set.
Exactly. Instead of pruning.
Yeah, so they tested a few different ways. This was one of them. And so I mainly talked about this one because this is the one I understood. But there's a few different ways that you can put data. So there's only one metric that you can think of to determine how useful a point is, right? Because it's almost qualitative to talk about how useful some data point is compared to the rest of it. Yeah. Yeah, I guess that's my answer.
Any other questions? I think the questioner brought up boosting as another strategy.
Yeah.
Which is aligned to pruning, but a different model. So yeah, I think classical machine learning has looked at a lot of these, but it's interesting to see how they're relevant to current techniques in language models.
Yeah.
Let's thank Arnav for his presentation. We'll move on to Conrad.
So hi guys, I'm Conrad, and today my presentation is on FlashAttention, which will allow you to scale and have faster and more memory efficient attention without approximation. So maybe let's go through some of the key issues with standard attention, right? So I have here a reproduction of basically the main way that we calculate standard attention. So the idea is you load Q and K like from your high bandwidth memory, then you compute S, and then write S back to the high bandwidth memory. You read this back again, afterwards you compute the softmax of that, you write that back to high bandwidth memory, so on and so forth. And basically, the key problems with this is that first of all, it has a ON squared memory usage where n is the length of n is the sequence length of your model, right? So because the memory usage kind of scales quadratically with sequence length, is quite a large bottleneck if you want to train larger models. And second off, because you're continually like computing and then writing your results back into high bandwidth memory, right? There's a lot of this like unnecessary I/O, right? You keep calculating stuff and then you keep writing back into high bandwidth memory. So these are two of the main so-called inefficiencies with the way you do standard attention, right? And the key idea behind this paper is that they look at these two bottlenecks and they find a way to remedy these two bottlenecks. So first off, right, the first question is, okay, can we avoid storing this ON squared QKT matrix in memory, right? Can we compute O without materializing the QKT matrix? So he uses this term materialize a lot in his talks. Basically, it means without computing the entire matrix and storing it back into HBM memory. And second of all, you want to minimize HBM accesses as much as possible, right? You want to avoid this whole like unnecessary loading and storing back into GPU memory. Yeah. So the key results are this. So previously in week 5, there was a lot of presentations on like approximations to attention, right? And all these different approximations, yeah, okay, they help you with more, they help you like maybe makes it more memory efficient, maybe it makes it faster and all that. But the key difference with flash attention is that it's not an approximation at all. It's exact attention with ON extra memory for computing attention instead of ON squared. And because of the way that they've done the computation, they've actually reduced the amount of times you need to do this like read and write between HBM. And now you have faster inference and training overall. So the key implication is this: you can now train even bigger models faster with flash attention. So maybe let's go into the first bottleneck and like how they've managed to solve this bottleneck. So, okay, suppose for the sake of explanation that we live in a magical universe where O is equals to QKTV, right? We don't have the softmax term. For now, let's just assume that we don't have this softmax term. Our goal is to do this computation without having to store this QK transpose matrix into our high bandwidth memory. So the question is, can we calculate O without storing QK transpose into our high bandwidth memory? And the answer to that is yes, with tiling. So tiling is basically just computing by block matrices, right? So what I have this entire diagram here. This is reproduced from the paper, but maybe I think it's better if I draw it out a bit, right? So basically, this is our Q matrix, this is our K transpose matrix, this is our V matrix, and this is the output that we want to get. Normally, when we compute attention, what we'll do is we'll take Q times this K matrix, and we'll have this humongous matrix, and we'll store this entire matrix into our high bandwidth memory. But instead, the key idea behind like this tiling is that rather than doing this whole thing, actually we can just compute results bit by bit and accumulate into O. And by doing this, we'll actually have the same result as if we let's say we compute this entire big matrix and multiply it by V. So what do I mean by that? Okay, so let's say we block this up into different blocks, right? Different blocks, right? If I want to compute this first block of O, what I can do is this. Let's say I hold this block of K constant first, then I do I hold this block of K constant first, then I take Q, I take V, I do the matrix multiplication, and I save it onto O, right? And let's say, then the next part, I do this, I hold this block K constant, I take the next block of Q, do the whole multiplication, and I save it to the next block. So previously what I was doing was I saved this entire matrix into memory, I multiply it with V. Now instead what I'm doing is I save like these small blocks at a time, and then I accumulate my results. So you can see how the memory usage is different, right? So in this case, originally I had this entire matrix, this is like O(n)². But if I chunk it up into blocks, then these blocks are like quite small, like definitely much smaller than O(n)². So this is like the key idea that allows us to actually save on the memory usage, right? We do the same, this is not really updated, I was editing it a bit just now, but basically it's the same computation, but done in such a way that the memory usage is different. And this is what allows us to save memory in the flash transformer. So tiling allows us to actually avoid materializing the entire QK transpose matrix and allows us to save memory. And the most important, I guess one of the reasons why tiling is also good is that having by being able to chunk up our matrices like this and like do the computation block by block, right? We can set these blocks to be of a size that is like small enough to be stored into our SRAM. So I didn't really talk about this just now, but yeah, our SRAM, basically the memory hierarchy of a GPU is like this, right? So I guess if you compare to like a CPU, your SRAM will be like your registers, and then your GPU HBM will be like your DRAM. So basically, accesses to DRAM are slow. Accesses to your high bandwidth memory are slower than accesses to your GPU SRAM. So if you do tiling, you can actually store all of these matrices in your SRAM, and you do all your computation on the chip itself, rather than have to keep like, after I'm done with this, I load everything back to high bandwidth memory, I load it back in again, so on and so forth. So, and in terms of actually how they implement it, in the paper, they actually have like a fused CUDA kernel, which allows them to have like this like fine-grained memory access and minimize like the read-write operations to the high bandwidth memory. But so this makes sense if, let's say, our attention mechanism is like this, right? We don't have the softmax term. But we do live in a world where the attention mechanism is actually has this softmax term, right? And that's problematic because softmax so-called couples the entire row. I can't calculate softmax without knowing like, what's the value of this entire row, right? So just now when we were using like I guess linear attention, right? We could basically calculate like block by block. Whereas now if we have softmax, we basically have like and this entire row is coupled. So we have to calculate this entire row first before we can calculate like what's the actual result of this supposed to be. And that's not ideal, right? Because now if let's say we want to do tiling, right? We want to do the same thing where we break up this huge computation to small computations. We can only go like row by row, right? And the idea was that we want to fit all of these blocks of data in our SRAM so that calculation is fast. So can we still do tiling with softmax? Are we able to, despite the fact that there's now this softmax operation in between our matrices, are we able to actually break it up into, are we able to break it up in tiles just now and do that same computation? And the answer is yes, which brings us to the second idea of this paper, which is online softmax. So you can prove it with a bunch of like boring algebra, but essentially the key result is this, right? If I want to calculate the softmax of A1 concatenated with A2, I can first calculate the softmax of A1 and and calculate the softmax of A2 and up to some scaling factors alpha and beta, this will actually give us the correct result, right? So essentially what this means is that it allows us to like iteratively build up the softmax from like blocks. It allows us to tile. And in order to do this, like the implementation, they go into more details of the implementation in the paper. We just have to keep track of like ON number of statistics. And this will allow us to actually tile our softmax computation. So overall, the extra memory usage is still ON, which is still better than the original memory usage of the standard attention transfer. The overall memory usage is still ON, which is still better than the ON squared memory usage of the original implementation. So putting the ideas all together, we can do the forward pass like this. Okay, first we load the inputs by blocks from HBM to SRAM, and then on chip we compute like the attention output with respect to that block, and then we update the outputs here by scaling. Right, basically we just sort of accumulate the computations like this. But then, so that's the forward pass, right? What about the backward pass? Because at the end of the day, I'm still trying to do training, right? In order to do training, I need to have that. I need to be able to know, okay, how much do I update my my QKT matrices by, right? If my backwards pass still needs like my QKT matrix to do back propagation, I actually haven't saved any in memory at all. I still have to store like matrices on the order of like ON squared, right? So you have here is like, this is the standard attention backwards pass algorithm. You see all of these like DP matrices, DQ, or DP matrices, DS matrices. These are still on the order of ON squared, right? So what's the trick to compute the gradients without actually having to store these kind of ON squared order matrices? So the key idea is basically this. Rather than actually like storing the matrices itself, we just recompute the backwards pass, right? About a whole bunch of like boring algebra and like math or whatever, but basically by saving the statistics, right, which again is on the order of ON, you can actually just recompute the updates. And even though you're doing more computation, right, because you're reducing the amount of high bandwidth memory accesses, it's faster overall. So basically what the author is saying is that in attention's case, right, the IO is the bottleneck, not the computation cost. So you can see here, right, the results in terms of speed, right? So he compares flash attention to a standard attention, right? Even though flash attention uses, even though flash attention has like more computation overall, you see it's like 75.2 compared to 66.6, it's somehow able to have like a runtime that's like a sixth of the standard implementation. And this runtime savings comes from the fact that you are reducing the amount of like unnecessary IO accesses. And in terms of like actually training BERT labs, right, you can see that flash attention, at least when they published it, they actually were able to outperform like NVIDIA MLPerf and like all of your different implementations of BERT. So that's the results in terms of speed. Now the results in terms of scale, right? So previously I mentioned that, okay, flash attention allows you to go from ON squared extra memory to ON extra memory. So what this means is that basically because you're using less memory than before, you're able to scale your transformer, to longer sequence lengths than before, right? Previously, maybe you've only like what, 4K fit in your memory, maybe now it's like 8K or something. I don't know, some math, but yeah. So what this means is that the memory savings actually allows you to train the first transformer that's capable of getting better than random performance on these like long sequence benchmarks. You're able to scale up your transformer to such a point where previously these benchmarks, right, transformers can't even perform like better than random, right? Now you're able to perform better than random. So the essence of flash attention is this. It's a smarter way of computing attention that saves you from having to store all of these like big matrices into your high bandwidth memory. It minimizes like all these redundant read and writes to a high bandwidth memory. It's more efficient and it's faster as well. And the key idea behind it is like these three main tricks, right? Tiling, online softmax, and recomputation of the backwards pass. And because of this, like because of this ON extra memory usage as opposed to ON squared, you're actually able to scale transformers to even longer sequence lengths than before. So when you read like Tridal's paper or you watch a lot of the talks he gives, his main point is this, right? Algorithms should be more IO aware. You should know like what is the IO cost of your operations, right? So the distinction he makes is this: what operations are compute bound versus memory bound, right? Attention is like fundamentally it's a low rank matrix multiplication, right? Because your Q matrices and your K matrices are like, I guess you can think of they're very like slim boys, right? So like when you do it, it's like it's a low rank matrix multiplication. So fundamentally, this is more of like memory bound as opposed to compute bound, because in terms of computation, you don't actually do that much. And I was originally going to cover a few more papers, but while I was preparing this, I realized I actually had homework due. So yeah, in the end, I'm only covering FlashAttention. But as I was thinking, as I was sort of like skimming through the other papers, I actually realized that, okay, actually, undergrad computer architecture OS has like a surprising amount of parallels with what you're doing in LLMs, right? So you can consider like FlashAttention as an application of like what memory hierarchy, right? So you know that accesses to slow memory like will eat up a lot of your time, whereas you should try to keep all of your computation using your fast memory as fast as possible. And I think later on William will be talking about this thing called page attention, and that's like direct parallel with this thing with the like memory paging. And I'm not sure if someone covered this last week. I remember seeing it in like the topics covered, but like there's this thing in like inference called speculative decoding, and you can think of that as kind of similar to like branch prediction. Yeah. So yeah, I guess that's more or less my presentation on FlashAttention. Do you guys have any questions? If you have any questions that I don't know how to answer, please, PhD students, high school students, and all freshmen, please help me with them.
Okay, let's thank Conrad for his presentation. Questions by anyone? So I agree that there are lots of things that if you pay attention to OS and CompArch, it can help you a lot with how things are. Of course, LLMs affect applications first. The people in our school that are worrying about architecture, they're of course worried about these types of things as well. And there's a lot of operations that are being done in matrix multiply that can be more optimized for the use case of LLM. So there's, I think there's still a lot of room for work and progress in that area. So especially for our undergraduates who are doing that, yes, there is, I think what Conrad says here is actually very, very much an area of work that the community is working on. So I also wrote on the Slack, since nobody seems to have any comments, that you know, these are things from an architecture case that don't take into account the actual use and the operations, the actual values that are computed with matrix multiply. So if you look at softmax, we're getting a speed up by algorithmic work, but it's more or less the exact value, right? If you look at the way that we actually use transformers and other things, there are other ways that you can optimize by doing approximate answering. Right? You don't need an exact value many times. You need something that's good enough. And there are lots of ways that you can do this type of optimization too when you forsake getting exact answers. The community hasn't really rallied too much around that yet, because people who do applications like NLP people don't usually talk to architecture people, even though we're in the same school, right? So that's true of research groups too. There's a lot of possibility for good interplay between that. Okay, so that's an area, especially if you're an undergraduate and you're taking all of these courses at the same time, you actually have more of a broader perspective than our PhD students, right? Because our PhD students are, by definition, trying to suffer permanent head damage, right? So they're much more narrow-minded in some cases, but that's sort of like by design. Yeah. Any other comments? Okay, we are really powering through. Okay, next section, please. Let's thank Conrad again.
Oops.
Yeah.
Yes. Thank you.
Yeah.
So hello everyone. We have been talking a lot about these deep learning models that are bigger in size, the bigger the better. And we have seen various ways how we can manage to build bigger models. And we have seen a lot of approaches, but I'm going to talk about parallelism in training. So by doing this, we are trying to build bigger models and applying parallelism while training the model. So I'm going to talk about model parallelism that based on two papers. One is GPipe, which has inter-layer parallelism, and Megatron LM, which has intra-layer parallelism. And then I'm going to briefly cover token level pipeline parallelism because I thought it was interesting to move from model to token level. So let's just dive right into it. I'm going to start with GPipe. Okay, so if you see on the left side of the first diagram, it shows basically it's an example of a neural network which is partitioned onto 4 GPUs, 4 devices, and stands for composite forward computation, and B is your backpropagation function. What you see is from every forward computation, the output goes to the next GPU, and then to the next, and then at the top you can see that the first backpropagation function takes the output from the device 3 forward propagation. So also every backpropagation function takes inputs from the previous backpropagation and the current forward propagation. Let me show you. Yeah, so this B2 is taking inputs from B3 as well as F2. So this is an example of a simple neural model. What we are seeing here is a naive model parallelism approach. What is happening is there is basically a mini batch of training examples. You can see that the batch, the first, this is, okay, to give you a better idea of timestamp and GPU, let me, yeah, this is better. What is happening is this first at the first timestamp, GPU 0 is processing this first batch of data. Then this data is forwarded to the next device as shown here. So this moves to the next timestamp, and this is processed by the GPU 1. Then the output from this is given to the next GPU and to the next. Then again to the next backpropagation, the outputs are given, and then it flows down this way. So you can see that at any given timestamp, only one GPU is active, and there is a lot of idle time. Also, yeah, there is a lot of idle time. So what GPipe proposes is it's a flexible library that is a pipeline parallelism model with batch splitting. So what it does is it breaks down, it assumes that a model is a sequence of layers, and it breaks down the mini batches of training examples into micro batches, and then partitions this micro batches across the devices and trains continues the training. I'll show this here. So if you can see, one mini batch is divided into 4 micro batches, and at the time when the first micro batch is getting processed, all the others are idle, the other GPUs are idle. But once this output is given to GPU 1 and GPU 1 is working, GPU 0 is not idle. It starts working on the second micro batch. It starts working. And same way, all the previous GPUs start working after giving the output to the next GPU. So basically we are reducing the wastage of time and idle time for GPUs. Also, you can see that the timestamp is now smaller than what it was before because we have broken down the mini batch into micro batches. Okay. So I'm going to cover some basics of the algorithm that is applied here. So sequence of L layers are partitioned into K composite layers or cell. Basically, every model, assuming there are sequence of layers, a group of consecutive layers are partitioned into cells, and then G pipe puts this K puts the kth cell on the kth accelerator. And the communication primitives are inserted at partition boundaries. This is to communicate between the adjacent GPUs. While forward pass, the G pipe first divides the mini batch into mini batch of size n into micro batches, m micro batches, and then these are pipelined to the K accelerators. For backward pass, the gradients of each micro batch are computed in the mini batch and processed. Yeah, at the end of each mini batch, the gradients are accumulated. So yeah, as spoken previously also, at each accelerator only stores the output activations at the partition boundaries. This saves memory usage. And while back propagation, to compute the gradients, the activations are computed again. So this is the accelerator recomputes the composite forward function. So this is reduction in memory usage. Although there is increase in computation, but reduction in memory usage. Okay. Here, if you see, we have some idle time where GPUs are waiting for inputs to do the next task. This is called a bubble. Basically, yeah, this formula here shows the fraction of time wasted on the bubble. So this top, the numerator is nothing but the amount of useful work done, and the denominator is the amount of time spent for each mini batch. So 1 minus the useful work is the time wasted on that bubble. Here, if you see, with one mini batch, the bubble fraction was 0.8, which is quite high. But when we divide the mini batch into micro batches, the bubble fraction becomes 0.42. So yeah, this is on bubble overhead. So there are some approaches to optimize the performance that are mentioned, as we spoke about gradient checkpointing. The activations are stored only at the partition and not cached throughout, because if you see, if we cache the activations, then the activation for F1 will be required from timestamp 0 all the way till 13, because B1 will be needing that. So we use gradient checkpointing, which we compute the activations during backward propagation. Memory requirement without this rematerialization and partitioning would be n into L. So number of micro batches into number of layers in the model. But with this rematerialization and partitioning, we have now the optimized requirement as n plus L by K into n by m, which is nothing but number of layers by number of partitions into the size of the micro batch. For bubble overhead, it is observed that this overhead is negligible when the micro batches are more than 4 times the number of partitions. This also might be because of the gradient checkpointing that we do, partially also because of that. Also, there is a very low communication overhead because we need to pass activation tensors only at the boundaries between the accelerators. These are the performance analysis. They tested it on AmoebaNet and transformer model. The one is without, on the right is without high-speed interconnect, and the left is with. If you see, with only one micro batch, the performance is not very appealing. But as you increase the number of micro batches across number of partitions, the performance is really high. With AmoebaNet, it is 3.48, and with transformer, it is 6.3 times. So that is a really good progress. And on without the high-speed interconnect, the micro batch size was fixed at 32, and it shows 2.7 times increase in performance for AmoebaNet and 3.3 times for Transformer.
Is that in seconds or what's the units for that?
Throughput, this is throughput.
Oh, throughput.
Yeah.
Okay, compared to just one.
One,
Okay.
yes. Okay, so we spoke about inter-layer parallelism. Now we will talk about intra-layer parallelism, which is breaking down the model into different devices, which is based on Megatron LM. So there are some limitations to some previous approaches that were taken, like the entire model must fit entirely on one worker, or a layer must fit, or it requires rewriting of the model, or it relies on custom compilers and frameworks that are still under development. So what Megatron LM does is it utilizes model parallelism to split the model across multiple accelerators. So this not only alleviates the memory pressure, but also increases amount of parallelism independently of microbatch size. If you see here, this is the transformer architecture, which has self-attention block followed by a 2-layer MLP block. So what we are going to do is perform like a vertical partition on both of these blocks, and thus achieve parallelism. So here are some calculations. Okay, so the top one is the MLP block. I'll start here. If you see, we have an input X. What we do is, so when we get an input, there are two approaches. One is to get parallelism. Either we can break the X, partition the X matrix column wise and the attention matrix row wise, and perform the activation, that is GELU here on that. So when you perform GELU on input and activation, after it is partitioned, you get X1A1 plus X2A2, right? Now the issue is, because GELU is a non-linear activation function, the GELU of X1A1 plus X2A2 is not equal to the individual GELUs, right? So we do not want that. The other approach is we partition the attention matrix column wise. So here, if you see, assume like this top part is on one GPU. Yeah, this, can you see the, okay.
You can press L if you want the right cursor.
Yeah, the top part is on one device and the bottom part is on the second device. So what happens is we replicate the input X. We have partitioned our attention matrix column wise. So we are doing now X1A1, Xa1, and sending it to the GELU, and we get the output Y1. Now this Y1 can directly be sent to the next layer without any communication between any devices. So this reduces the synchronization point. So we don't have to synchronize, it can directly go to the next layer, perform the matrix multiplication, and then after an all reduce, it can just be sent to the next layer. Same thing here. So this partitioning of attention matrix column wise is how we achieve this intra-layer parallelism. Similar approach has been adapted in self-attention. Here again, we have replicated the input matrix X, and the Q, K, V are partitioned column wise here. And then the same Y1 is output is received, and which is sent to the next layer. The only thing that is added in this architecture is we have all reduced per block. So here we have at the front F and then G, and again in the self-attention block. So two per block all reduce operations are added. This is the only change. Otherwise, the architecture remains the same. So this is based on PyTorch. So this is how we are attaining parallelism intra-layer. They have tested this on GPT-2 and BERT. I will quickly walk you through the analysis, the performance analysis. So this is the parameter used for scaling studies. Yeah. If you see, this is from top to bottom, the model size is increasing. The number of parameters are in billion. 1.2, this is the baseline model, which has 1.2 billion parameters, 1 GPU. If you see here, the model with 8 GPUs, this is model parallelism with 8 GPUs, 8.3 billion parameters. It achieves 77% of the linear scaling. So the baseline model was able to achieve 39 teraflops during the overall training. And this model, the 8.3 billion model, is able to achieve 77% of that with 8 GPUs. So this is quite a good achievement. And when we apply model plus data parallelism, which is dividing the data on multiple devices and processing, it gives, with 512 GPUs, there is slightly less performance than the model parallel because there is some communication required, but it is still 74%, which is a really good performance. Also here, these are the zero-shot results. So as the model size for 8.3 billion parameters model, the perplexity has reduced on Wikitext to 10.8 compared to the previous state-of-the-art model, and accuracy has increased to 66%. So this is on GPT-2. For BERT, when it was like 336 million or so, after that there was a paper published that it cannot be scaled more than that because there is a shoot up in model loss, like it's unstable, and it was just it cannot be scaled up. But this paper showed that by rearranging the layer normalization layer in the BERT model, it can be scaled a lot more. And here they have shown this after rearrangement and this approach that with 752 million parameters, the loss is increasing as the iterations are increasing. Also here there is a comparison of Megatron 3.9 billion model with other BERT models, and it is performing consistently better than others compared with when applied on development set results as well as the raised data set. Okay, so we have so far seen interlayer parallelism, intra-layer parallelism. Now this is about token dimension. Okay, here in this diagram, yes, here you can see all of these together. So this is quite a good diagram. How intra-layer was working, how interlayer was working, and then this is a new dimension of token level parallelism. Here, why this approach was utilized is they found a key observation was that whenever a tokens is processed, it depends only on the tokens that came before it and not on the future tokens. So there is a scope of parallelism there. Also, for the previous approaches, there were some limitations like communication overheads or reduced efficiency due to the bubble overhead and changes to the underlying optimization algorithm. This TeraPipe algorithm does not change the underlying optimization algorithm, but it is a dynamic programming based algorithm which gives out a optimal pipelining execution scheme given a specific model and cluster configuration. So we'll walk through. Okay, so I'll quickly walk through what is actually happening. For every hidden input state, H1 to HL, the self-attention of HT is basically only, it depends on all the hidden states before it. So from H1 to HT minus 1. And the feed forward computation depends only on that HT. The computation layer of Fi at any step T can commence. So the computation at I can begin once all I minus 1 steps are ready. So this can be parallelized with the computation of previous steps. So what happens is when I'll go here, what happens is when this device is performing operations on this, the next device can perform operations on the previous token, and then the previous, and then the previous. So this can go on, and this is how we can achieve parallelism. So the forward propagation time, Ti, for the slice Si on cell Ck is determined by the length of the slice, how much is the input, and the length of all the previous subsequences, and the basic cluster specifications. Here, if you see, whenever we perform these operations, we usually divide the tokens uniformly. But the first part, if you see, this is uniform division of tokens. But you see, the time required is not non-uniform. The reason is, if you see here, the process of performing operations on this token depends on so many previous tokens, but for this it does not depend on anything else. So the processing time is different for different tokens. This is why here it takes non-uniform time across all the operations. So the second this image shows, if you have non-uniform tokens processing, you can achieve uniform time across all the GPUs. So this is a key observation. They tested this on GPT-3 with 44 billion parameters and with 175 billion parameters. If you see these 1, 4, 8, 16, these are all uniform token distribution, and DP is this dynamic programming that is applied. So this has the lowest latency compared to the other uniform tokens processing. Similarly, with this bigger model, with dynamic programming, it has the lowest latency. So they have figured that the GPT-3 performs 5 times, gives better 5 times throughput with this DP applied. Yeah, this is the GPT-3, the 10th specification model. If you see here, this gives best results with this application. Even for others, with this DP approach, the latency has been decreasing. Okay, so that is it. These are some other papers that I thought were interesting, but couldn't get time to read, but I suggest you do if you get the time. That's all. Any questions? Yes.
So like token-based like parallelism, right? Because you see that.
Okay, for token-based parallelism, right? Because you see that, I think in the scribe notes, what I read was that it's because it is a casual relation, right? Like you realize that every token only looks back at the previous token, right? Or something like this. But they only works for decoder-based models, right? So if you only have like an encoder like BERT, can you still do token-based parallelism? Because in the encoder, you actually, your attention matrix, you look at the entire matrix, not just mask to like the previous tokens as well, right?
Right. I mean, this is based only on decoder only model, so I'm not sure.
Okay, thank you.
Okay, switch to the first. So yes, this one. Referring to the figure D, I'm wondering whether the space complexity will be O(n) squared, because on device 1 you have to store the key vectors, KV cache for every token before it, and on device 2 you need to store everything up to the second last token.
Yeah.
So it seems to me that there's a lot of redundancies in memory to store, right?
Yeah, so there is O of n square is the complexity, but they have right now I can't recall, they have implemented something that improves this the n square to something better, that I can't recall.
Gotcha. And does the number of devices correspond to the sequence length?
Right?
Or does the number of devices correspond to the sequence length? What is the relationship between the sequence length and the number of devices? So for instance, I have a sequence could be up to thousands of tokens, but I only have 8 devices. In this case, how should we do the level parallelism?
So that is what the dynamic programming, the code will do. It will give you a non-uniform sequence of tokens that you should send to the different devices. Suppose you have 8 devices and 8,000 is the sequence length. It will give you what is the optimal ordering and the non-uniform sequences to send to the GPUs. That is the code.
Could I just ask, because you're showing one of the papers, right? One of the papers you did not read or have is 0++, right? Deep speed, right? I'm just curious. I don't know how much you know about it. I'm just curious about deep speed versus like Megatron LM. Yeah.
Yeah, I'm sorry. I don't know about.
I'm not able to add a bit, but because I'm not really, I need to skim through it. But I think other than like these people versus Megatron LM, right? I think this bit there's like different stages, so you can choose which stage of parallelism you want. And then as you go up stage from stage 1 to stage 2, right? It tends to like shut more things and make more things parallel. So it becomes
Yes, I think from 3 to 2, there are 3 stages, right? So 3 is just the optimizer, 2 is the gradient, then 1 is the model. Right?
Yeah, correct. So I think like compared to Megatron, from what I understand, it's only just the model part, right? But it doesn't have the gradient and the optimizer sharding.
I see. Okay, yeah.
Because
because deep speed generates what the industry uses. And I think Megatron was very, very popular like a few years back, but then it gave way to the deep speed. I think also one of the extra things, I think, is it true that Megatron LM models trained on Megatron LM are only able to be used by NVIDIA Megatron LM infrastructure to inference?
I'm sure about that.
It's likely the case, yeah. But sorry, you want to say something? No? Yeah, I think it's good. If anyone wants to put up the paper for deep speed or any associated resources, then we can have an offline discussion on the general channel on that.
I think it's already on the randoms.
Oh, it's already on the random. Okay, so Warren's already posted on the random. So you want to discuss there, it's good to do that. So you can assign it as your recess week homework if you'd like. Yeah.
One of the things that differentiate between Megatron and deep speed is that deep speed is more on training side, where you short the automatic mistakes, whereas you can do Megatron, use Megatron for inference too, because they can short forward.
Can be more efficient for decoding as well on the forward pass. Okay, Disha, thanks so much.
you.
Yeah, thanks for
Oops.
Just click on the screen. It should go forward. Whenever you're ready, yeah.
So today I'm going to talk about after you train all your LLMs and how you're going to do inference on it. So I guess the first question we would like to ask is why is it so hard to do inference for LLMs?
Are you asking a question?
Yeah.
Okay, so guys, perk up. Go ahead.
I think it's the context length, right? You have a constraint on how much text you can give to the LLM, because we give too much, right? The n-squared attention algorithm will cause it to become very slow.
True.
Yeah.
That's yes, and I think context length is related to memory. So there's only so much you can fit into memory. So later we'll go through some calculation on how much how big a model you can fit into your GPU. Then of course, from the attention mechanism, is n squared. So we need a lot of memory for it. Another reason is because it's hard to parallelize, but I think Filbert is going to talk about it later. So because it's autoregressive, so it's hard to parallelize. So apart from running from multiple GPUs, what are some ways that we can make inference cheaper? I mean, we covered some of this already, so just feel free. Yeah, quantization is one. And this is like a bag of tricks. I think there's no it's tried and tested, but there's no standard way of making inference cheaper. People have been trying many different ways. So one way is to increase the arithmetic intensity. This is I'm going to talk about this later. Then other ways, kind of like modifying the model architecture. Then quantization, prune the parameters or distill it into a smaller model, so it can fit into your one GPU. So assuming you get this GPU, I'll give it to you, and you look at the specs. Let's say you get a 80 gig one. So what's the processing power? What's the compute of it? Let's say it's 20 teraflops, but then in comparison to that, you look at the memory bandwidth. It's only about 2 gigabits per second, right? So let's think about it. How much memory per second do you need to do we need to pull from memory to sustain this compute that your A100 can calculate? I mean, assuming like 4 in, 4 out, 4 bytes in, 4 bytes out, 8 bytes, we need at least about 160 terabytes per second. But if you remember, we only had the memory bandwidth is about only about 2 terabytes per second.
Gigabyte, right?
Gigabyte. Yeah. So this means that our GPU is memory bandwidth bound. So I think this goes back to a bit to Conrad's talk about FlashAttention. So how can we use our compute to the fullest potential? And one thing we want to do is to increase the compute intensity. So I think there's this webpage article is use the analogy of a factory. So think of your A100 as the factory with a very strong, you can produce a lot of stuff, but then it's limited by this conveyor belt to the warehouse. The warehouse is the memory. And so if you want to fully utilize your compute, you want to do as much stuff as in the memory, do as much stuff in the factory as much as possible. And you can do that by reusing the data value and doing a lot of calculation here. So for example, in this simple function, is this repeat? How many times you can repeat that calculation before sending it back to memory? So related to this is the roof-like model. So at certain point you are bandwidth bound, but once you pass it, you are compute bound. So you want to try to be compute bound to fully utilize your A100. Then so let's do some more calculation. So how much memory do we need for inference? Nowadays LLMs are billions of parameters. And each of them is a decimal number, and assuming it's stored in B float 16. How much memory do you need to load the weight for Falcon 40B? Yeah, I think it's
80 G.
80 GB. Yeah. So this is just to load the weight. You use up almost all of your memory VRAM in your A100. So how are you going to do inference at all? So let's kind of review attention. So this is attention. I guess everybody knows about this, and assuming that the sequence length is 2448 and we have 64 heads. So to store the QT matrix, how much do we need? I'm just going to go through. So you need another about 262 megabytes. But this is only for 2048 input tokens. What about longer text? There are many tasks that requires longer text input, such as REG, or even with a chatbot, you need to store the context of your chat. So so you need much more longer context length. So for example, what if I think GPT-4 you get 32K context length right now, and so that's about 131 gigabyte, I think, if my calculations are not wrong. Yeah, so we covered the large memory footprint, and so what we want to do right now is to think about how we can reduce this memory required. So the first paper we're going to cover is page attention, and one of the key thing we're going to talk about is the KV cache. So the KV cache is, because it's auto-regressive, we'll keep on using the same K and V values. So it's only efficient to cache that KV. I mean, yeah, cache that KV. And once we do that, we only require to keep those in memory, the number of generated tokens. So the amount of memory that we need is only increases linearly, and it increases the compute efficiency. But keeping this KV cache in VRAM can be very expensive, especially if you have like a 32K input sequence, and you have no idea of how big you're going to allocate, how big a cache you should allocate for a KV cache, and it can grow, it can shrink, because you never know what's the input sequence going to be. So so you can see here, assuming your A100 VRAM is 40 gigabytes, more than half of it is used to store the parameters. Okay, KV cache is about 30%, and you get like about 5% for others like activation or something. So this is not ideal, and so for existing serving inference models, what this paper says is that they are very inefficient. There's tons of different types of ways that memory can be wasted. So if you look at this picture at the bottom, there's three ways, there are three types of memory ways that they were talking about. One is you reserve it for future. So in your VRAM memory, first you reserve it for the KB cache. Then there's also internal fragmentation and external fragmentation. And existing systems cannot exploit the opportunity for memory sharing. So page attention and VLM makes the suggestion that why not we use something like virtual memory with paging in operating system. So how does, well, I'm not a systems guy, but how does, from what I understand from how virtual memory with paging works, you have a lookup table, then you kind of like store the address in the lookup table. So this is the same idea is used here. You have your logical part and your physical part, and so you partition your KB cache into fixed size blocks, and you store it in non-contiguous memory space, and then the kernel will identify and fetch the different KB blocks from a lookup table. So this will make it very efficient because you can now store your KB values in not continuously. So this is the attention calculation for the per key block, and this is how you kind of calculate the attention weights for each block using the query vector. Yeah, and this is the block table where you have where you kind of look up the address in the physical KB cache blocks and kind of use it to fill up the logical KB cache. So now this memory is allocated on demand, and you see VLM compared to other serving systems, it's very efficient. There's hardly any wastage, but other systems have a wastage of they use like 20% up to 20% of their of the memory efficiently. So that's one of the benefits. Increased GPU utilization. Apart from that, you also get to batch more, because the memory is smaller, you get to batch more things together, and you get enhanced throughput and all this good stuff. And maybe one thing is you get to share prompts. So for example, you have this shared prompts, and you have like, so you can set, you have two different sequences, but you have the same starting prompt, like the future of artificial intelligence is. So you get to share this memory sharing. You get to use memory sharing to generate the subsequent tokens for two different sequences. So you get to share memory and save memory. Yeah, so you get to reduce the memory usage by up to 55%. So this is all very well and good. But then, did you really decrease the KB cache size? Although now it's breaking up into different blocks and used more efficiently. So for Falcon, this is the model card for Falcon 40B. You see it has a 60 layers. The dimension is 8,192. and has 64 hits. So the KV size, KV cache size for Falcon 40, if you calculate theoretically, it should be around 4 gigs. But if you look at the actual KV cache size, it's only 240 megabytes. So what else is it causing the memory savings? Yeah, so I want to go back to the roofline model. So now that you reduce the memory size, you kind of like increase the operational intensity, and so you increase the amount of compute intensity, and that's one of the benefits of using page attention. So the second, apart from page attention, another thing that you can use is multi-query attention. But first, let's look at multi-head attention. If you remember the original attention model, transformer model, they talk about the multi-head attention, where H is the number of copies of this matrix. So in multi-query attention, the key intuition is that we don't need so many heads. Why not we just use one head, one for K and one for V, and share it throughout. So by doing so, you reduce the amount of memory needed by a factor of H. So if you reduce the number of heads, obviously the amount of memory needed will be reduced. And thus the amount of you increase the amount the compute intensity. Another benefit is that you also will allow us to increase the batch size, which in turn also allow us to increase the amount of compute intensity. So in the paper, they show that there's not much difference between multi-head attention and multi-query attention for inference. For encoding, I'm sorry, for encoding, but for decoding, there's a huge difference. But of course, this comes at a cost, because you only have one head, and having more heads, you actually can capture the more complex relationships in the data. So, a very natural extension to the idea is, why not we use more heads, but still very much less than the number of heads that we use for Q. So this is kind of like the middle ground between multi-head attention and multi-query attention. So this is quite a recent paper, I think, and I think this figure kind of explains it better. So multi-head is where you have one head per query, one value head and one key head per query, and multi-query you only have one. So for in-group query you have more, and you share it. So let's look at the benefit first. They also found that you can actually uptrain a train model to use this kind of reduced heads type of attention, and the inference speed is comparable to multi-query attention. But then because you use more heads, the performance is better than multi-query attention, and much more closer to multi-head attention. So how they do it is they kind of like min pull the projection from the KV matrix, then you continue to training for 5% of the original training steps. So 5% is they kind of found out 5% is sufficient. yeah, this is the performance. So 5% is, you kind of get the performance of a multi-hit attention here already. So I think that's all. So I think the key idea here is how to reduce the amount of memory that you need to use for your inference. So you can fit into one GPU. And yeah. Any questions?
Guys look all burnt out. Yeah, go ahead. Yeah.
So, just asking, why does fragmentation actually affect like the memory constraint? Like, how does it actually affect? And yeah, like for the page attention part, yeah.
I think because if you kind of reserve it for, like you reserve this part for future tokens, you kind of like block it out, and so it's very inefficient if you want to calculate other tokens.
So basically, like by using a page attention, right, you break it down into like smaller blocks, right?
Right.
Then, like at the end, right, the last block, won't there also be some kind of inefficiency? Because if it doesn't use up the whole page, right, then it will still be inefficient, right? In that case.
True, but compared to the current way of doing so, is much more efficient.
Okay, thank you.
So another thing I want maybe to add on is that I think you can use flash attention and page attention together, and so it doesn't have to be either or. You can kind of use it together. So this is kind of like a bag of tricks that can use. So you can use flash attention with page attention with multi-hit, multi-query attention to get a lot of memory savings. And I think group query attention is pretty new. So that Llama 2 is the only one that is trained using that. But yeah, but Falcon is using multi-query attention, the one with one hit.
The 180 also using, or is it just the 40 dB?
Which one?
180 query attention.
Multi-query attention. Yeah.
Is it the Falcon 180 dB or the 40?
I'm not sure. I haven't read right into whether that, but I think the 40B uses. Yeah.
Other questions? I think the key takeaway from these sections is, a lot of our architectures and our hardware doesn't age well. So if you come back and watch this video 2 years from now, we probably all laugh that we're thinking of envying A100s, right? Because it'll be outclassed very soon. The key ideas are to think about whether you're memory bound or compute bound, right? And I think also energy bound, right? Because we don't want to consume so much electricity. We haven't really talked about any of these constraints from the papers we talked about so far today. Keep that in mind. I mean, when there's a new architecture outside of transformers that comes about, we have to go back and revisit all of these issues. So as soon as somebody comes up with a new architecture, you can get your first NURIPS paper quite easily, right? Because you can just redo all these experiments for that architecture and get paper.
There is the retention by Microsoft, like I think published in July.
Yeah, so it seems to happen. It doesn't take long, right? I mean, yeah, so you can think about trying to catch up, right? And like I tell my group all the time, you think about the next advance when those advances are already out. Because if somebody's made a new architecture, it's probably somebody working on a model architecture is probably already somebody trying to optimize hardware. So what comes on the next line after that?
Yeah, a lot of these tricks is focus on the attention mechanism. That's why maybe based on another architecture, you do have to find another ways to do it.
I think someone also did try to do something in positional embedding. I think it's called yarn. The paper is called yarn, and then basically they try to increase context size by manipulating the
Yeah.
the row potential. No, the row position embeddings. Yeah.
Yeah. So yeah, one of it is like extending. I think it's rotary and memory.
Yeah.
Yeah.
Then someone did an extension
Extension to
that's
that,
called
yes. Yeah. So this is inference on one GPU. I think Filbert is going to talk about multi GPU.
Okay, let's thank William for this segment. Oh, yeah, sure. Please go ahead.
For the presentation, I'm wondering how does the page attention help to increase the GPU utilization? Also, I understand that it can help to increase utilization for the GPU memory. How does they increase the compute utilization? Does it?
So you're sending, so the amount of data you're reading from memory is smaller. So you're not constrained by the amount of memory bandwidth anymore. So it's like sending small amount of data over to the factory to be processed. So that's kind of like helping to increase the amount of compute intensity.
With reduced fraction, you're like you can increase the arithmetic intensity by.
Yeah.
Gotcha.
Yeah.
And how does the reparameterization help to increase the arithmetic intensity? I'm not quite sure about this concept. So
Okay. Yeah. All this I think is I think it's also used in FlashAttention, tiling, and reparameterization. So I'm not quite sure, but I think like you only calculate the forward pass, then calculate the gradients back. The backwards pass gradients. Is it or what is it?
FlashAttention, I think they increase the arithmetic intensity just by like reducing the amount of memory reads and writes.
Yeah. So
Can you paraphrase? Because I don't think I'll pick it up. Yeah.
Yeah. In FlashAttention, they kind of, I think this is a similar idea. They're trying to reduce the amount of memory reads and writes, but in
I'm not sure how like page attention works, but as long if you just don't have to read as much in, then your arithmetic intensity will increase just by the fact that like you're doing the same amount of computation, but like it's spread out over less like memory reads and writes. But I'm not very sure if that's the case for page attention.
So remember you have a lot of compute like I think it's 19 teraflops. So you are willing to spend a bit more compute to calculate the backward pass for FlashAttention, and then so you kind of try to keep all this in the faster SRAM. So it's kind of like this is what, from my understanding, what is reparameterization is. So you compute all of those that then you send it back to the slower VRAM.
Okay. And by the way, we have invited the lead author of the page attention, TerraPad, and our professor, which is Johan, to give a talk online next Friday at 11 a.m. So feel free to ask Zoom link for me.
Yeah, it's okay. You can actually post it on.
Sure.
Yeah.
Happy to. But that's in Mandarin speaking.
Yeah,
So if
yeah.
you don't mind.
You can just say okay in Chinese. Yeah.
Thank you for the opportunity.
Okay, we have our final speaker for today.
Hi, I'm Filbert. Because I'm Gen Z, I'm allergic to capital letters, even for proper nouns like my own name. Because I'm also Gen Z, I'm gonna post for the picture that Isong's gonna take. You take picture, right, for all the presenters?
I haven't today.
Never mind. I'll post for now.
I can do that. 1, 2, 3. Thank you. I post.
Okay, so I have like 9 minutes to present my 20-minute presentation. I'll
You
do
have
what I
20
can.
minutes to present your 20-minute presentation.
I'll do what I can. If you're gonna go, you're gonna go. It's chill. So let's do a quick recap on like why we are here today, right? Today we talk about scaling, training, parallelism. So in the beginning, there were language models, and then people were like, hey, if we make the language models bigger, then it will perform better, right? So then the AI scientists, they were like really caught up with this idea, and they just started making bigger and bigger and bigger models. And then like somewhere along the way, like our models got too big to fit in a single GPU. Then they're like, okay, let's just throw more compute, let's just throw more GPUs, right? So they just kept doing that. And then like systems people, they were just sitting there and just looking at like, what are these guys doing, right? So that's why we've seen all these cute little bag of tricks so far that we presented, how to make like expensive operations less expensive, like most notably attention, right? We've seen different ways to make attention cheaper, as presented by Conrad, as FlashAttention, as presented by William, there's your page attention, multi-query attention, blah, 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 and so on. And also, because now we're using a lot of GPUs and everything, so there's also a lot of different ways we can like schedule our tasks onto different GPUs and so on. So basically, it's also important to consider like the more systems aspect, which is why like the entire all the talks today so far have been on a systems level. So great. Today I'll be talking about parallelism in inference. So it's a more like production-based view on it. Cool. You're not gonna get me with this, Warren. So all these slides today that I'm gonna present assume we are working exclusively with this decoder-based models, right? Yeah. Can. Cool. So first things first, let's talk about inference, right? Inference is an iterative process. So you are given like a prompt, an input, and then you have to generate a bunch of tokens for the input until you're done, right? So you do that, you can only do that one token at a time, at least for now. There's speculative decoding, which approximates a bunch of tokens at a time, but let's not go into that today. So let's assume we're doing it one token at a time, and in each iteration, you generate one token, then you auto-regress on that token that you generated, and so on and so on and so on, until you finally generate like an end token that basically says that, hey, we are done generating an output for this prompt, right? So inference is iterative. And we should also consider what is the key differences between inference and the training workload, right? Because in training, what we want to do is we want to update our model parameters based on like our training data. So the workload is very fixed, very standard, because you know how big your training data set is. In contrast, when you're running inference, at least like in a production environment, you are trying to make predictions based on unseen data. And because you are serving your model to clients, basically like your workload may be very unpredictable. Maybe like depending on the time of day, you might get more requests for inference as opposed to other times of the day, right? For training, you need to do the forward prop, the back prop, and then do gradient descent. For inference, it's just forward prop. You just want to generate the output and that's it, you're done. And the main objective of training is to minimize training loss. Whereas for inference, because you're dealing with a client environment, you want to maximize throughput and minimize latency. Fun fact, I used to think throughput was pronounced taraput until like yesterday. So yeah. Cool. So let's think about how we can do inference in practice, right? So assuming like you're OpenAI, you are making this thing called ChatGPT, and you made like a web platform that people can use to send prompts to your GPT model, right? So you can model inference as like a client-server kind of process where your client sends a request to the server and the server sends a response back to the client. And if we think about it in this manner, then basically what we're trying to do is construct a server, like a good architecture for the server that can handle all these requests efficiently, right? So most commonly what we'll have is sort of a serving engine, which will basically take in all the requests, and then your serving engine will distribute all these requests to your different devices. So your devices like your GPUs will be running your models on execution engines like TensorFlow, TVM, PyTorch, TensorRT, and so on and so forth. And your serving engines will be things like TensorFlow serving and the Python inference server. There's of course more, but I'm not going to give you an exhaustive list on that, partially because these are also the only ones I know. Ken, as mentioned, performance metrics. What's throughput? What is latency? Throughput is basically how many requests you can handle at any given time. Latency is roughly how long it takes between receiving a request and completing it. So of course, there can be like different definitions for this, but I'll just be working with these high-level ideas of what throughput and latency is. Right. So let's understand how scheduling decisions work. Consider this example where basically my client has a first request, right? What is the capital of India? This goes into my serving engine. And for at least for the serving engines that we've seen, like Triton or TensorFlow serving, what we'll do is that we'll actually batch a bunch of requests together if they come in like within a short enough duration of each other. So like in this case, if a new request comes in, request 2, what is your name? We can actually batch request 1 and request 2 together and then send that to our model for inference, right? So in this case, what we get to do is, the reason why we do this is, the reason why we do this is because our GPUs can run a lot of computation in parallel. It's very good at doing that. that's actually why it was built for, right? So if you don't like batch your requests together, then you're kind of missing out on this parallel potential that the GPUs offer. So let's see what are some of the issues when you actually batch requests together and handle them. So firstly, we have latency when returning. So consider this, right? Suppose GPU 1 is processing this batch consisting of request 1 and request 2. Request 1 is what is the capital of India? And the answer is just New Delhi. Whereas request 2, what is your name? Then you'll say something like, my name is blah, 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 blah. So in this case, if we consider like the way batching works, you only generate like one token at a time for each of these responses, right? Together. But by the time you're done with request 1, you still have a bunch more tokens to generate for request 2. You're not done with request 2 yet. But the thing is that because it's in a batch, you can only like receive the request and return the response in batches, meaning that I have to wait until my request 2 is done, until I can return request 1. So clearly this is bad because like, why shouldn't I return request 1 right away? I'm already done with it. There's latency between finishing request 1 and returning request 1, right? So this is bad. There's a latency here when returning. And what's another form of latency that we have? There's a new latency when considering new requests. So again, consider the same example where my GPU is processing request 1 and request 2. And now, at this time, I also receive a new third request, right? Request 3. What is 1 plus 1? Unfortunately, because my GPU 1 is already processing this batch, right? It cannot accept any more new requests. So that means that my request 3 will not even be considered for processing until this batch completes. So this may be bad. Like maybe if in your production environment, you have like a way to prioritize certain requests, this will not be able to handle that, right? Even though maybe like your request 3 might be of higher priority than request 1 or 2. So basically, to sum up, latency when returning responses and latency when considering new requests. So these are problems introduced by batch level scheduling. And what is one solution for this? Well, by the Orca paper, they introduced this thing called iteration level scheduling instead. So it's a pretty simple idea. Basically, instead of scheduling by the whole request, by a batch of whole requests, you schedule by iterations instead. So let's consider this example again, which are slides that are effectively copied from the author's presentations, but let's not worry about that. So the scheduler receives 2 requests, right? R1, what is your name? R2, what's the capital of India? This goes into the request pool, and since the model is free, basically you schedule these 2 for execution, right? So now you will generate 1 token. R1 generates a token mine, R2 generates a token new. And then this goes back into the request pool. At the same time, my scheduler receives the request 3, what is 1 plus 1? So because we schedule by iteration, what this means is that after my model does exactly 1 iteration for request 1 and request 2, we consider it done. We'll throw it back into the request pool. And now I can schedule request 1 or request 2 or request 3. So as you can see, this already solves that second problem of new requests won't be considered, right? Because now after 1 iteration, my request 3 can potentially be scheduled in the next run, right? So for example, like this. So now let's say in this next one, I schedule request 1 and request 3, right? So again, 1 iteration and back in the request pool. And now let's schedule again, request 1 and request 3. Now request 3 is done, right? Because 1 plus 1 equals 2, we generate 2, we generate the n token. So what do we do with request 3? We can actually just return it, right? We're actually done with that already. We don't have to wait for a certain batch to be done. So this is like the advantage that you get with iteration level scheduling. Because you schedule by iteration, you have more granular control over when you schedule new requests and when you return already completed requests. And let me just finish this. Yeah, and you return. So yeah, as mentioned, more granular control. You can return completed requests as soon as they're done, and you can begin to process new requests as soon as they arrive. But of course, when you schedule stuff back and forth, you keep putting things between the model, the request pool, the model, the request pool. You incur a decent amount of communication overhead as well as like overhead from running the scheduler, right? Because the scheduler isn't like a trivial algorithm. Like there's like a bunch of stuff you need to consider when you decide which request to schedule next. Yeah. So there's more overhead there, and you also kind of lose on the benefits of batching, right? Or do we? So actually, no, we don't. So yeah, let's review what batch operations are. And basically, it's in order to batch like your tensor operations, like let's say your attention or your matrix multiplication or your layer norm. Normally what is done is that you need to standardize the shape of all your tensors, right? So if you schedule by batches of requests, then that's very easy to do because they'll all always be in the same iteration. and they also all have the same shape because you can just pad them and then suddenly they're all standardized, they're all ready to go. But when you schedule by iteration, then what you'll notice is that actually like you might have requests at like different stages of processing. Like maybe one of them has 4 tokens generated, one of them only has 2 tokens generated. And then this, you won't be able to like pad it and everything and basically batch that operation. Like there's difficulties there, is what I'm trying to say. So what is the solution for this issue? Well, as presented by the authors of the Orca paper, they introduced this thing called selective batching. So maybe you can't batch attention because attention doesn't work that way for reasons that are beyond my understanding because I'm new. But you can still batch like other operations like non-attention matrix multiplication or layer normalization or like the feed-forward passes lah, basically. Yeah, so the simple idea here is when you have a bunch of other, you just split your operations up into batchable and non-batchable. And then for the batchable ones, because they don't care about like your shape, you can just concat and just run them together. Then when it's time for attention, you just split it up back into their constituent segments. You run the attention individually on each of those, and then you concat them back again once you're done with it. So here is a slide I stole from the author's presentation, where basically, yeah, so for stuff like layer, norm, and linear, you can just slap all these tensors together into like one concatenated tensors. And then you can actually just run these operations without caring because they just scale well like that. Whereas for attention, you have issues. So here's another slide I stole where basically they just split it up, do the attention individually on like these chunks, and then you can merge them back for like the next level of processing, right? So with these simple ideas, there's actually like more techniques that we use in Orca because Orca is supposed to be like a solving engine. So it's kind of like a product of sorts. So there's more techniques being used here, but you can see like how like this simple idea of narrowing down like your granularity from batch level scheduling to iteration level scheduling allows you to see performance increases like that. And in this case, even though there's more overhead introduced from like the scheduling and communication overheads, the fact that you can schedule, the flexibility you get from scheduling by iteration kind of outweighs that lah. And they do have results to show for it. Just a quick summary of some of the other techniques that are used in Orca. So they also do the model parallelism, which I think was introduced by Disha just now. You split your models, the intra and interlayer parallelism. Yeah, so you split your models and different parts of different layers of the models can run on different devices, right? Intra and inter-operator parallelism. Next, because as we mentioned, you need to split your attention stuff. So you need to keep track of all the QKV matrices for all your different attentions, right? So they also introduced this thing called the attention key value manager to basically handle that part, the details of which I will not go through because I also didn't understand it. Because Orca is a serving engine, so they also deal with this thing called a master worker architecture, right? So the master or the scheduler decides how to allocate the tasks to the workers. So because you have these and because you have multiple workers running in parallel, what you can do is that you actually have this pipelining effect, which is also similar to what I believe Disha and William talked about, right? You did talk about pipelining, right? No, you didn't. Okay, my bad. Sorry, wrong guy. Yeah, the point is that you do have this pipelining effect because you can just do it on multiple devices now. Yeah, you get the point. Yeah, you're smart people. You get the point. TLDR, here are the results. Basically, Orca is saying that you are good because even though, okay, so these results, this first part doesn't consider scheduling at all. It just considers like how efficiently how long it takes for your workers to process the inference request, right? And basically what they found is that even though, because we use selective batching, even though we aren't able to batch the attention operation, we are still able to achieve pretty good comparable results to faster transformer, which is like their baseline paper for comparison, right? And now if we consider like including the scheduler and everything, and you talk about throughput and latency, the results basically show that you can achieve, like for the same compute budget, right? You can achieve either better throughput or better latency or both. Yeah. Okay, so that's pretty much my presentation. Very simple high-level ideas here. I didn't go into the math also because like there weren't a lot of math, and also there was one paper that talked about queuing theory for some reason. I don't know what that is. Do you know there's math about queues? Yeah. Anyways, yeah, thank you. That's the end of my presentation. Don't ask me questions, I'll cry.
Okay, questions that are not hard.
Hi, yeah.
The Oka model, right?
This is
it's the Oka serving engine.
Oka serving
Because
engine.
Microsoft also is the Oka large language model.
Completely different.
Oh. Yeah. Okay.
Different Oka, different Oka.
Okay, thanks.
Yeah. Oh yeah. I was about to talk about another paper called El Paso, but also I ran out of time, both like presenting wise and like in reading a paper. But the high level idea for that is that I also decided it wasn't very applicable for today's class because like basically what El Paso is statistical multiplexing for language models, which is like only effective when you're considering like multiple different models. So like if you want to like do inference for like multiple different models, you have an environment where you need to take requests for different models, then AlphaSurf shows a performance benefit. But like if you're considering just like one model, it doesn't have results for that. So I thought it wasn't very relevant for today. Yeah. But yes, more questions, if any. No?
Questions?
No?
Okay, that's
Cool.
thank Filbert.
Clearly that means I did a good job. Thank you, everyone.
Don't quite leave yet. I've got 3 minutes for you. So if you go back to our general channel, you can go to the sheet. All right. And despite the nice portrait pictures, we need you to again fill out your team ID if you haven't already. Okay. Since we've gone through most of the first half of the course in quotation marks, then you should be able to fill out some of these parts. So if you haven't already, you should complete your self-assessment for the segments that you've done, either lecturing or support. So if you haven't done that, you can do it actually right now. Why not? And then do fill in your self-assessment hours for your projects. You know, you've excuse me, at least done iteration 1 for your project and you've thought about it. If you've secured compute and you've actually done some experimentations, or if you've just sat down coffee, tea with your friends who are helping you with the project, then count that in, okay? I am quite liberal, and yes, I know it's on record, with the hours that you put into the course, okay? The whole point is, again, I really don't care as long as you get exposure to LLM and that we have more of a base of people who at least have reviewed some of the materials so that we can have a base to work from, okay? And again, part of the reasons for this course is to network all of you. So you might bump into each other later on. Oh, I took 6101 before. I might have seen you in network. I'm actually having lunch with 2 6101 grads that went into our course 3 years ago, and we were doing reinforcement learning. So that was completely different. But I'm seeing them next Wednesday. So please do this so we can certify, especially for those of you who are internal and doing it for credit. But again, people external to the course who are external guests, please do it as well. Okay, one other thing. I said 3 minutes. It's going to take another 2. Let's see whether we can go to. Which is next week. We actually don't have class because it's recess week, and we put preliminary project reports here. So we are off next week. If your group happens to want to check in with me, you're welcome to. I will make a schedule available. It won't be recorded, even though it's at this time. It's only going to be for the first hour for me, but I may make the hour before. That means 3 to 5 o'clock available for people who want to meet. Okay, because I have to attend fundraising events for SOC in the second half of this time slot for next week. Okay, so keep up the good work. I hope you guys are making progress on your projects. Even if not, that's okay. You know, the point is to try to get yourself some exposure. All right, any questions? If not, let's go. Thanks, everyone.